For the Bellringer, it says imagine you're around Gliese 832. This is a star which is located approximately 16 light years from Earth. The Gliesians have built a telescope which they will see through objects with infinite resolution. If you were to point the Gliesian telescope at Earth and looked at a calendar, what year would the calendar say it was? So this has to do with the limited speed of light. So if someone were, right now, somebody on this planet were to point a telescope at Earth and they could, zoom in and see objects with infinite resolution, they would look at the calendar and they would see a year that was 16 years ago, right? So they would see, March 29th of 2005. Is that right? 5 plus 16 is 21. Yeah. So they would see 2005, which is the year some of you were born, I believe. So, they could theoretically see you, as like a newborn. And that's what really they would see. They would be seeing into the past, right? For us, our past, but their present. And this has to do with the finite speed of light. This is true. Anytime you look at an object, if that object is, let's say, 20 light years from Earth, and you're seeing that object as it was 20 years ago. If an object is a million light years away, you're seeing what that object looked like 1 million years ago. Today, it probably looks drastically different, but that has to do with the finite speed of light. So when we look at objects that are further away, we're really looking at things looking further into the past. So as you look further and further back, you can look further in the past. And there's a limit to how far we can see, right? And that is what the part of what the cosmic microwave background is. It is the limit at what we can see. We can't see anything further than that light. That's the furthest light that we can see. Now, again, it's not visible light today. It's been stretched out over time. So originally, it was visible light, and it was light because the universe was so incredibly hot. It was so hot that it was just glowing. They called it in that video an orangish color, right? But over time, those waves have been stretched out so that today they're not visible. When we look out into the night sky, we see darkness. I mean, obviously you see the stars, but in between the stars you just see darkness. You don't see any light. If you could see in the microwave portion or the radio portion of the visible light, or of the electromagnetic spectrum, you would see that glowing. You would see everything glowing, but we can't see that. But radio. And we have radio antennas that can detect it, and that's exactly what happened to Penzias and Wilson. So one of the reasons why the cosmic microwave background is such a big deal is because it's the leftover light that we can still see coming from everywhere in the universe. And it's the oldest light that we can see. We cannot see any light older than that, because before that, the universe was in a state where it was sort of this big plasmic entity. So basically, things couldn't travel very far because of all the free electrons that were roaming around. All right. Today we're going to talk about the Big Bang Theory itself, like what exactly the theory lays out. The first thing I wanted to talk about is who proposed. So it was proposed by a Catholic priest. I looked up how to pronounce this earlier. Okay, so I don't like French very much, so it's hard for me to pronounce this. But it's Georges Lemaitre. So Georges Lemaitre was a Catholic priest in 1927. He was a physicist, and specifically, he is what you would call a cosmologist. Cosmology is the study of our universe and its history. So he was, in 1927, the prevailing theory was that the universe was static, that the universe was unchanging. So things didn't change. It kind of all stayed the same on large scales. So the universe was, number one, infinite. So there's no limit to and there's no edge to it. Just goes on forever. And again, number two, the universe was static. It did not change. Okay. Lemaitre proposed this theory, which said that the universe instead had a beginning. At the universe, there was a moment of creation or a moment of start that the universe started. So he really, I think, really was a fan of this theory because it supported his Christian beliefs. To him, this is sort of victory for his religious beliefs because if the universe has a start, right? That's what his religion said, that there was a start to the universe. And that's what he proposed. He said the universe has a beginning. It's not always in constant forever there, but the universe has a beginning. And again, I think it's interesting that today, I think that a lot of religion and the Big Bang Theory sort of clash. But originally, at least in the eyes of George Lemaitre, they were really in sync. This is exactly what he wanted. He had a scientific theory that matched up with his belief that there was a beginning to the universe. And that's what the Big Bang says. The Big Bang says that about 13.7 billion years ago, right? 13.7 billion years ago, everything, the universe as we know it, would have been squished down to the size of even smaller than an atom. Now, naturally, we want to ask the question, but what was before then? What was before everything was like an atom, right? Because, it's fine to say the universe started then, but what happened before that? What set off the Big Bang? What put it there in the first place? Where did all this stuff come from? Unfortunately, this is an answer that science can't give us right now. We don't know. There is no scientific answer to what happened before the Big Bang. The scientific answer is that time itself started at this moment. And before then, it's philosophy, right? We don't have an answer. The reason why we can't really give an answer is because of how intensely, just how much energy and how intense this moment was, okay? I mean, think about for a second, this classroom, right? Imagine if I had everybody in the school, if I said everybody in the school needs to go to my room and we were going to shut the door. I mean, you'd probably imagine it was impossible, of course, to get everybody in here. You're probably right. It probably was impossible, okay? That's just the people in this room. That's the people in this school to fit in this room. When you start to talk about every single thing that exists, and again, we know about so little that exists, but all matter that exists, being in the space smaller than an atom, to say it's extreme is understatement. It's like, what I'm trying to get at is our laws of physics don't work at those scales. When you have so much stuff in such a small area, we cannot tell you. I mean, the physics doesn't work. We don't know what things would act like at that time. We don't know what would happen. And so that's why, if you want to ask before, okay, what happens before, the universe begins, there's no answer. We can't give you one. It's somewhat unsatisfying, but that's it. There is no answer to that question, at least no scientific answer, at least yet. Maybe some kind of breakthrough will happen. But on those scales, it's just so much that our understanding doesn't work. So the point is that the universe, like everything that exists, was still there. Okay. Now I want to clarify: it's not matter at that point. I'm going to talk about it in a second. It's just energy. The universe is entirely energy, and it's all energy concentrated into an infinitely small point. Then something happens, and the universe itself begins to expand. Now, that's sort of the Big Bang, right? It's not this one-time event, right? The universe is still Big Banging today. It's just getting bigger. That's all that's happening. It's just an expansion. Now, the expansion starts out incredibly fast. In fact, there's this period called inflation that happens shortly after it starts. And if you look up this stuff, you're going to see it gets quite complex, right? I mean, there's a lot of complexity to these different, they call them epochs. So there's like the Planck epoch and the quantum epoch, and there's all these different times. But what we're interested in knowing is the basic idea that at the beginning, the universe is incredibly small and it's all energy. And then there is an expansion that occurs. Okay, about 3 minutes after the Big Bang, the universe has grown a lot. Okay, it's gotten a lot bigger. And what happens is you get the first particles start to form. Okay, and this is where we should talk about the equation E equals mc squared. No doubt you probably heard of it. It's like the most famous equation in the world probably because Albert Einstein came up with the E equals mc squared. Reality is it's kind of like part of an equation. There's actually a lot more factors there, but it still holds up pretty well. E equals mc squared. In this equation, there are different parts. So E stands for energy. M is mass, and C is the speed of light. Now, if you remember, the speed of light is 3 times 10 to the 8th meters per second. Okay? So the reason why this equation is so famous and so radical is that Albert Einstein, his equation says, you know what? Energy and mass are the same thing. It's a bold claim, but still true. Energy and mass are the same thing. They can go from one to the other. So you obviously are made out of matter, some stuff that has mass, but you could be converted into energy somehow. And if you were converting energy, it takes a lot of energy to make a little mass, because think about what you're doing, right? You're taking mass and multiplying it by the speed of light squared. That's 3 times 10 to the 8th. If you square that, that's 9 times 10 to the 16th. That's a 9 with 16 zeros. You take a little bit of mass, multiply it by 9 with 16 zeros, and that's how much energy you get back out. It is incredibly huge amounts of energy. In fact, the most powerful weapons that we have, right, nuclear weapons, atomic weapons, they use this same process. They take, right, we're going to talk about eventually nuclear fusion and nuclear fission. It's the idea of taking mass and converting it into energy. And just a little tiny bit of mass can create a heck of a lot of energy. It's a whole lot of energy. So, going back, there's so much energy in the universe. It's so hot that mass cannot exist. It is all energy up until this point. About 3 minutes after the Big Bang, you get the very first particles start to form. They're not in atoms yet. They're just particles that are around. It finally, so remember, as it expands, the average temperature is going to go down. Eventually, it's sort of like energy is freezing into matter, right? Energy is sort of, as it expands enough, a whole lot of energy become a little bit of mass, a little bit of stuff. And so the very first particles are formed. Okay? But the first atoms don't really form at this time. You have nuclei that are forming, but because it's so hot, the entire universe is a plasma. When I say a plasma, it's another state of matter. In a plasma, the electrons can move around freely. So you have the nuclei there, but the electrons are moving around freely. That's what was happening in this scenario. And so that's why you couldn't see anything. That's why it's called the dark age, because you can't see. Light cannot travel very far. However, a couple 100,000 years after the Big Bang starts, again, after that expansion starts, it's still going on, still expanding. The temperature has finally cooled off enough that you get neutral atoms form, that you get atoms of hydrogen and helium forming. And it's that moment, right? That moment, the glowing of the universe. Finally, as those atoms form, light can travel through the universe quite some distance. And that's the light that we're seeing. So when we talk about the cosmic microwave background, the CMB, the reason why that's such an important piece of evidence for the Big Bang is because that's the light that's predicted, right? And actually, this light was predicted before it was discovered. If you remember, it was discovered about 1965. Well, Lamartine came up with his theory, the Big Bang Theory, in the late 1920s. By the 1930s, people had already expected to see this cosmic microwave background. They said, we should be able to see this light, but we haven't found it. So a lot of people said, well, this is evidence against the Big Bang Theory. It's not a good theory because we predict this evidence, but we can't find it. So when Penzias and Wilson discovered that, they were awarded the Nobel Prize. Not because I would say they were awarded the Nobel Prize because they found a piece of evidence which is strongly suggested and now has actually been found. And that's actually a pattern that you see happen in science quite a bit. Somebody will predict of something that should be there, and then it will be a long time before somebody finds it, right? So the first person, neutrinos, were something that were predicted as just a particle. They were not found till many, many decades after the person who predicted them passed away. Recently, you heard about, maybe in the news, gravity waves. There's these gravity waves that we can detect. They were predicted by Albert Einstein. They were discovered about 3 or 4 years ago. So this happens time and time again. There's a prediction made, And we're limited by our technology, but once our technology gets good enough, we can all of a sudden find those evidence that was previously predicted. So the cosmic microwave background is the light that happened right when this was occurring. When atoms finally formed, it's that last bit of light. It's that light that the universe had because it was radiating because of its temperature. And it was visible light because the universe was still very, very, very hot, even several 100,000 years after the Big Bang. So when that light came through, that's what we see when we look up at the sky and see the cosmic microwave background. The early universe was about 75% hydrogen and 25% helium. It's still very similar today, right? Today, it's still about 75% hydrogen, about 23% helium, and then 2% everything else. So again, most of the stuff that was formed, again, it matches very well. Another piece of supporting evidence for the Big Bang Theory is that the universe is about pretty close to what was predicted. Okay. About 200 to 400 million years after the Big Bang starts, you finally get the first stars and galaxies start to form. So stars are mostly hydrogen and helium, right? We're going to talk more about them later, but they undergo this process called nuclear fusion. Nuclear fusion is where stars basically take pieces of atoms, smash them together, and create heavier elements. So for example, you may notice here, hydrogen has 1 proton. Helium has 2 protons. The process is a little bit more complicated, and we're going to talk more specifics later, but nuclear fusion is where a star takes hydrogen and slams pieces of hydrogen together to make helium. And in that process, there's a little bit of mass that's lost, and again, that mass is converted to energy using E equals mc squared. About 4.6 billion years ago is when our sun and our universe started to form. We'll talk more about this number later and see why, but just for this, in terms of the scale, universe is about 13.6 billion years old. That means our solar system is fairly young, all things considered. Okay, so the misconceptions here. The first and most important is that there was no explosion. There was and continues to be an expansion in the universe. That's all the Big Bang Theory really says, is that the universe is expanding. Which, again, we talked about how Hubble measured the Doppler shift in galaxies and found they were all moving away. If you go backwards, clearly they're all coming together, and that's where this idea of an expansion comes from. Okay? So again, it's not an explosion, it's just an expansion that still is continuing today. The universe still continues to expand. Also, excuse me, I think we tend to think of imagine something out in space and then it just kind of blows up. But everything, space itself is inside of what with this singularity, this Big Bang singularity, this small, infinitesimally small point that begins to expand. That's space itself. Prior to that, there's no space, there's no time, there's no matter or energy, nothing, right? So again, prior to that, we can't even explain what was there because again, the tools that we use to explain that break down and don't work. Okay, so that's pretty much what I want to show you. Again, this infographic here is pretty good. I know it's kind of small on the screen up here, but you can pull it up on your own. The point is that this is a lot of things happen really quickly at the beginning. This is the pattern. The pattern is you go from small to big. So at the beginning, it's all energy. There's so much energy that nothing is even nothing can exist in terms of matter. No particles. It's just energy. So as it expands, it cools off, and you'll see here the temperatures continually decrease. Okay, but as it expands and cools off, matter starts to form. At first, you get what we call quarks, and then quarks form into the basic protons and neutrons. Those basic protons and neutrons eventually start to form atoms. Now, you get the nuclei first because it's a plasma, but then eventually, that's 3 minutes. So again, all that happens in the first 3 minutes. And then, eventually, 300,000 years approximately later, they combine. So the electrons and the nuclei combine to form the first atoms of hydrogen and helium. That's where the cosmic microwave background comes from. Then those atoms start to combine, eventually start to coalesce and form stars. Those stars eventually come together to form galaxies. So it's this sequence where you go from the smallest to the biggest. Now, what's interesting is thinking about the future. Okay, well, so we know maybe about the past, but what does this tell us about the future? What's going to happen to our universe? There are several different theories about what will happen in the future, and it all depends on, there's a couple of pieces of data that we need to determine. The most likely situation currently seems to be what's called, it's okay if you giggle at it, called the Big Rip. The Big Rip is where instead, so the universe is expanding, but that expansion accelerates. So the big question is, okay, what's happened to this expansion? Is the rate of expansion the same? Is the rate of expansion getting bigger, or is the rate of expansion decreasing? If it's getting bigger, which seems to be the currently what we think is happening, then the universe will continue to get further and further apart. You'll notice that the temperature keeps getting cooler. Eventually, the universe will entropy is what we call this state of this idea that energy is spreading out. Eventually, the universe, as it gets bigger and bigger, the density, the temperature, the energy density goes down to almost nothing, and the universe will become 0 degrees essentially. That's called the Big Freeze, and that's what's most likely to happen if the expansion stays the same. If the expansion speeds up, which is what we think, then before the universe sort of freezes off, the expansion continues to get so fast that things start to literally rip apart. You kind of go backwards, right? So galaxies start to fall apart, stars start to fall apart, planets will fall apart. Literally atoms will start to tear apart eventually. Now that happens, again, that's way, way, way in the future. I don't know off the top of my head, maybe very far. So you see here, they're talking about 15, in the future here. I don't know how many billions of years, but definitely tens of billions of years. The last is if the expansion actually slows down. In fact, it could reverse, right? The idea is it could reverse where the Big Bang, so it's expanding, but then eventually the expansion stops and then actually starts to come back together. Gravity pulls everything together. That's called the Big Crunch. Again, if we look at the data today, it seems to suggest the Big Rip is the most likely possibility, but of course, data is found all the time, so we don't know for sure what will happen.